they're showing on that round piece, they're showing the torque going like that, right? On that first between, well, the first pulley on the left, and they say it's 4 kilonewtons or 4 kips inches, right? Now, to me, the internal torque would have to be going in the opposite direction because it's resisting. And that's not what they showed in the answers for the answer key. They showed it going the same way. I don't agree with that. The internal torque should be the opposite.
I don't think
I'm saying it should.
no, they didn't give us a direction.
Right, but in my answer key they did. And it's a resisting force, right? So if this is the input, then this should be the internal torque. It should be just the opposite, because it's resisting the output or the input force. So, but the book, the answers didn't quite show up that way, and I don't agree with that. I think it should be the opposite. I mean, that's just like saying that if I've got that. Remember, we had we had a force that was going down on a beam, let's say. Well, what were the reactions doing? They were going the opposite direction. Okay, so that internal force has to be the opposite direction. So same thing on the torque.
So it should have been a negative number. Is that what you're?
No, it would just be, you would have to indicate the direction in a different,
Oh, okay.
like in this case, if we were looking straight in at it, then this would be, to me, this would be the resisting force. Clark?
So I have a question. For example, at B,
Mm-hmm.
the answer is 13, right?
That's correct.
I mean, why is it that you can say that internal stress at B is 13 where you've added the 2 numbers to the left rather than the 2 to the right? Like, is that a real?
Well, but let's look at that. I'm glad you asked, because, and I'm just going to draw this like a stick figure, if you will. So you got these two. This one is 4, let's say, going clockwise. This one is 9 going clockwise. Then you got this one over here, which is 18 clockwise. And then you got this one at 31, but it's going counterclockwise.
Well, it comes out the same if you do it right.
Yeah. So if you cut it right here and you look this way, it's 13. If you cut it here and look this way, if I can borrow my drafting, it would be 31 minus 18, right? So yeah, there's a 3 and a 1. And this was 4 plus 9. Can I do that backwards?
Yeah, that makes a lot more sense then.
Okay. Yeah, it's because this one was going the opposite direction, so they counter each other. So see, you weren't the only one that had that question. So that's pretty cool that we could get that straightened out easy enough. So case in point, though, you got to watch what your directions are doing, don't you? On a problem like that, you have to make sure, you're not always going to be adding. So,
But what keeps like me looking at it one direction and you looking at it from another direction?
doesn't matter. But if you cut it, when you cut it, you have to look one direction or the other, and whatever you only deal with whatever the input forces are from that point to the left or that point to the right. Okay. Yeah.
If you cut it at C, depending on if you look to the left or the right, you get opposite direction.
Yeah, but you still
Answer.
get the same numbers, don't you?
The same number, but opposite directions for the internal torque.
Mm-hmm. Well, let's see now. If you, yeah, but you're looking at the opposite direction. The thing is, the shaft, that bearing, or that shaft would still be turning one direction. It's just saying that, okay, so there are belts on all those pulleys, right? And they're going to different types of equipment. Well, what this is saying is it's taking 31 kips inches of torque. In other words, that thing's got more drag on it than those other things going the other way, is what it amounts to. And it can still be turning in the same direction, but you've got a monster machine or some kind of motor or something that is picking up that power off of that 31 kips inches. Okay, that's a monster machine compared to those other three that it's turning, or motor or pump or whatever. So they can all be turning the same. It's just like on a car. You know, your cam is turning that flywheel, right, which is turning all your different accessories. Well, they're all running off of different amounts that it takes, power from that shaft. They're not all taking the same amount of power. Your alternator, is taking some power. Your water pump is taking some power. What else? If you've got an air conditioning unit on there. In fact, that's why a lot of guys go to electric pumps, because it doesn't take power. All the power is going through the alternator, isn't it? You're losing all your power there, which is negligible compared to if you had a mechanical type pump working on that, or fuel pumps, same thing. So, does that make sense, Clark?
Yeah, I guess the internal resisting torque, the direction doesn't matter.
I think it matters. But it depends on which way you're looking at it.
Yeah, if you're looking at it this way, then the rotation is going one way. If you turn around and you're looking at the other direction, then it's going the other direction. That's good.
Well, but the rotation
not
could
what I
be
mean.
the rotation could be going either way there. But it's just the way the machines are hooked up to that shaft. I mean, in other words, you could have or the way the direction would have to be the same, but you've got the 31 kips motor would be back, if you will, behind you, the way you're looking at it, and the other pieces would be on the other side. The torque's going to be the same no matter how you look at it, because it's all turning in one direction. That shaft is turning one direction, period. So the torque, it's all going one direction, but it can be varying amounts and still hold true. So
I
Yeah,
just
but-
mean, if you were going to give a direction in your answer, then you were doing point C.
mhm.
If you looked at the ones to the left, you'd end up with the opposite direction in your answer than if you looked at the one to the right. That's
Well,
what-
let's see. If we looked at the ones to the left, whoops, what happened? If we look at the ones to the left, we decided they were all going this way, right? Then if we looked at the one to the right, the input torque is the opposite, right? So we're saying that our output or our internal would be going that way, right? Okay, so but this is left looking right, right? This is right looking right. But if we went and looked at that from the other side, which way would it be going? If we reversed this, it would be going like that, wouldn't it?
Physically, it's still the opposite direction. I mean, there are two different directions, Yeah, you can look at them from both sides, but it's
Yeah.
two different things.
Yeah. I see what you're saying. I don't know that. I guess the book isn't wrong per se, in the fact that, that does throw it. And we don't really even know. I mean, the torque the input torque is doing this, but that doesn't mean the shaft is going that way, but it's still, to me, the internal force is going the opposite direction, but it can't go the opposite direction in the same shaft. Although, I don't know, I'm going to have to ask somebody about that. I'm going to have to do some more research, because that, yeah, how can you have it, it's actually doing two different things in that one section.
You know, I'm confused.
Yeah, but between right in here in C is the question. What's going on there? This one's going the opposite way. Well, it's not turning the opposite way, but the torque is doing the opposite. So I'm going to have to check. I'm going to talk to Mike and John about that, because that's an interesting concept there. Yeah. It would almost be like it would double it up, which we know that's not the case. So we'll have to see. Do some more checking. Okay.
We know how to
But
get the numbers.
yeah, the main thing is right now for the test, you just have to, if you cut it and look at one direction or the other, just add and subtract them based on what the torque's showing you. If they're going the opposite direction, you have to subtract them. If they're all going the same way, you have to add them. So for the test, okay, that's all we'll worry about as far as that goes. Especially since I don't have a good answer for what the direction is going to be doing there. Okay? Now, let's see, what about 12.2? 12.2 is similar with the exception of it's anchored at one end, right? And then what they don't do for the torque internal for A, what they didn't do is there's something, well, actually on that pulley they give you the torque, but they're not giving you the torque at A, so you just have to know that you've got one kip times 18 inches. And remember, it's the force times the distance. It's one force times the distance. So inches. So it's 18 kips inches. And personally, I don't abbreviate that kip. They did in the book, but I just like to see it. If you don't spell out kips in your homework or in your test, I won't count wrong. But it should see kips in inches if that's the units.
So when we got the equal and opposite forces, that's called a couple.
That's the couple,
Use
and you just
the
use
diameter.
one force and the distance between.
the distance.
Yeah, because see, that's really not diameter there.
No.
If it were a steering wheel, it would be. But that's
how I was thinking of it. But
Yeah.
let's say you only had.
this is a drag racing car. It doesn't have a full steering wheel.
Okay. Let's say you only had, one force on one side, not the other side. You use the
Force times distance. You'd only have one force, right? So yeah, like if you were doing a torque wrench type thing, it'd still be force times distance, but you just have one force and one
9
distance.
inches instead of 18.
Do what? Well,
The distance would be.
realistically, you wouldn't even have to worry about that other side of the handle, right? If you only had one, yeah. If you didn't have both hands on the wheel, if you will, if you only had one, then yeah, it's only going to be the radius times the hand that you've got doing the work, right? And again, think of it in terms of a breaker bar or a ratchet, or just a wrench in general. Most wrenches don't have two sides to pull on, do they? So it would just be force times distance, and you'd only have that one. But you could have two hands on it, but you're only applying force in one location. So as far as the couple is concerned for what we're doing, think of it in terms of that. You're only going to be putting the force on one location, but it's spread out over the full distance. So it's force times distance in either case. But couples, you only use one force. Okay? Essentially, on a couple, or think of it in these terms. You're only applying one kip. You're just using two places to apply that one kip, aren't you?
Right, so really you got half a kip here, half a kip here.
Pretty much, yeah. So that's what I would say there. Yeah. For a couple. Let's see what. Then the second part was what? Well, the internal at B is going to be the 18 kips inches plus we were given that the other one was 100, right? So you got 118. Easy enough. Just add them up. They're both going the same way, right? That would be the only thing I would suggest you would have to be careful of is make sure that if you had that couple, you know, if we looked at that same picture and the torque was going this way, but instead of the couple going this way, like that, which is essentially the same way, right? If we changed that up on the test and made that couple do this, we went this way with that couple, you're going to have to subtract, aren't you? That would be the only thing I would caution you about when you're doing any kind of a problem. Okay? So if they had reversed the arrows on that one kip, you'd have to subtract that 18 from the 100. And that would have been the only difference. Problem 3. Calculate the maximum shear stress developed in a 3.5-inch diameter circular solid steel shaft subjected to an applied torque of 5,000 pounds-feet. Well, first part of that, you just have to find the polar moment of inertia, right? Pi times the diameter we're given, that's 3.5 raised to the 4th power divided by 32. Find out that that's 14.73 inches to the 4th. Stress in the steel is going to be equal to the torque times the radius, if you will, C, divided by J. The torque, wasn't that given? 5,000 pounds-feet. Okay, multiply that by 12 inches per foot, so you can get it into inches, times the radius of 3.5 is 1.75, divided by 14.73 inches to the 4th. And you should come out with 7128.3 PSI. Pretty straightforward. Looks like the common reoccurring theme here is we've got to find the polar moment of inertia in about every one of these problems, don't we? From the start. So keep that in mind when you're doing your quiz. Quiz, right? I've been calling it test, haven't I? I'm supposed to call them quiz. That's my rule. If you call it quiz, then people don't get all shook up. As opposed to a test, you know. See, if you can't get test anxiety if you're taking a quiz. And you might get quiz anxiety, but
Okay.
you like the way I think, Chris?
Same difference.
Oh. Okay, so the next one then, 12.5. Let's see.
Can you give me the answer to 12.4?
12.4? I can give you the answer. Let's see, it's calculate the allowable torque of a hollow steel shaft. Inside diameter is 40, outside is 85. The allowable shear is 68. So let's see, I can cheat here and look, but basically it's the same type of issue, isn't it? For 12.4, We have to find polar moment of inertia. That again is pi diameter, and we had 80, 85, and 40, right?
Yeah.
So 85 raised to the fourth minus 40 raised to the fourth divided by 32. Now, according to the chart, I don't have my calculator, but according to this, it says it's 4.87 times 10 to the what? Sixth millimeters to the fourth. Okay. Then from there, what are we looking for? Torque. Yeah. Torque is going to be what? The stress, steel allowable, times the polar moment of inertia divided by the radius. So let's see, the stress we were given, weren't we? 68 megapascals. 68 times 10 to the 6th pascals is what they did here in the book, times 4.87. And the reason they went to pascals is because of the millimeters, right? Because isn't the megapascals, what's that, newtons per meter squared, wasn't it?
I thought it was
Mega? Mega was millimeters?
Yeah.
Well, in which case this would just be, what, 68 times 10 to the third? Huh? Or just the 68, yeah. That's. I don't know why they changed that then. Well, no, let's see. This is, oh, you know what? That wasn't considered 4.87 times. Well, yeah. That's what he did. I skipped a step here. And then he went in there and changed this for whatever reason. I don't know why you would have to do that. To 4.87 times 10 to the negative 6th meters to the fourth. Why couldn't we have just left that in millimeters? We're going to try that here. This is what his answer is. Times 10 to the negative 6 meters to the fourth divided by this is crazy. 85 divided by 2, which is the radius, right? But then it's times 10 to the negative third meters. I don't know why he went to meters on that.
Yeah, I didn't do any of that.
Okay, so, well, let's, but I'm going to do it with millimeters here in a second. So then his answer is 7.79 times 10 to the third Newton meters. Well, no, that does. And then he goes back and changes that to kilonewton meters. Well, that is the kilonewton. That's 7.79 kilonewton meters. That. So if we didn't change that, it would just be what, 68 megapascals times. What's that going to be then?
4.87 times 10 to the 6 millimeters.
Yeah, because that's still millimeters, isn't it? 87 times 10 to the 6th divided by 85 divided by 2. What's that? 42 and a half? What's your number come out to?
I got 7,800 Newton meters written down there.
Well, what's that right there? That's right there, isn't it? Do what?
No, I think I just multiplied mine by 1,000.
Okay.
Or divided. You know, it's going to be 8 millimeters to meters. I didn't write down that last step.
But this is all millimeters here, right?
Yeah.
So you ended up with what on this?
7,800 Newton meters is what I have written
Okay, so it'd be 70, 79.
All my calculations are in millimeters, and then I got Newton meters.
If you punch that in, it comes out to 7.79 times 10 to the 6.
Okay, that's what I was looking for on the answer. $7.79 times 10 to the 6, is that what you said? Okay, and that's what? That's going to be Newton millimeters, right? But then we need to get that into Newton meters for torque. So then you'd have to multiply that by,
Divide by 1,000.
Divide by 1,000.
Make it 10 to the power.
do what?
You consider we change it to 10 to the power of 3.
Yeah.
Okay.
So basically the same numbers.
Yeah, it's the same thing.
Yeah.
I didn't write down that last conversion from millimeters to meters in my worksheet.
I was like,
Okay.
why don't we subtract the two radiuses? Like the C,
Right here?
you know, like for the torque, we have two different, we have an outer and an inner radius.
Well, you're finding the max, right?
Oh,
So the max is always, if you're not finding the max, then you can go somewhere else and look. In fact, one of these problems did that, I think. Was it 12.8? Yeah. I asked you to figure out the stress in the inner and the outer, but if you're finding the max, it has to be at the outermost, right? And that goes back to that one drawing that we had where the shaft looked like this, and how did they draw that? Was it through the middle? Where you had a situation like this where it was less the closer you got to the center of the shaft. Right, actually, I went too far there, didn't I? It should have been at the center. Okay, you get the point. That's when we looked at that the other day. That's where that's coming from. So you want to find the max there, and that's the worst case scenario. You got to find the max. So that's what we deal with. Okay, 12.5. Let's see. Calculate the allowable torque that may be applied to a 5-inch diameter solid circular steel shaft if the allowable shear stress is 10,000 psi. So that one, again, you just figure out your polar moment of inertia. This one's an easy one because it's solid, so there's your polar moment of inertia. 61.36 inches to the fourth. The torque is the allowable stress times J divided by C. That is 10,000 given, right? Times 61.36 divided by 2.5. And that's 245,440 pounds inches. That 245,000 sounds like a big number when it's pounds inches, though. That's not near as. If I was pounds feet, you'd have to get an awful big wrench. Okay.
Is it typical to convert that to pounds feet when you got such a big number like that?
I would say that would probably be my typical. Yeah, I mean, yeah,
That's
because
what I did.
yeah, it's. But it depends on what. Well, I guess, yeah. If that's being used, like if you're having to tighten something up, if you have to use a torque wrench,
Yeah.
then you're probably going to definitely want to convert that to pounds feet, because most of your torque wrenches aren't going to be in that,
Well, yeah,
when
my small
you're talking
torque
about
wrench doesn't go up
pounds,
to
inches,
45,000.
yeah, you're not going to have. But if you change that to pounds feet, yeah, it might be easier to come up with a good reading. Okay. So yeah, it's just scary, isn't it? What did you convert that?
Yeah.
Well, what did it come out to?
20,450
Yeah.
pound feet.
That's still a lot.
Yeah. My
That's-
torque wrench don't go up that
No,
high either.
no. I think mine only goes to 100 pounds feet. So, but that's only a 3/8 drive. So, but we're talking about different types of mechanisms and stuff on this. So that's what
You're
we.
not tightening that down by hand.
No, no. Yeah, you're using some kind of electric, probably, or something like that. 12.8. Calculate shear stress in the outer and inner surfaces of the hollow circular steel shaft subjected to the torque of 350,000 pounds-inches. The outer diameter of the shaft is 6 inches, the inner diameter is 3. So, again, here's our J, polar moment of inertia, pi, times 6 to the 4th minus 3 to the 4th, outer minus the inner, divided by 32. That ends up being 119.3 inches to the 4th. And the shear on the inner is going to be the 350,000 times the 1.5, that's the radius, right? Divided by 119.3. And that turns out to be 4,400.7 psi. And what do you think the outer is going to be? About twice that, huh? Coincidentally, but wasn't there some kind of a linear proportionality thing on that? Didn't we talk about that? The outer stress, 350,000. 3. That tells you right there, doesn't it? I mean, that's the only number that changed. 8801.3 psi. All there is to it. Now, if you were going to practice a problem for that last section, it would be anything from 1219 to 1225, wouldn't it? If you're going to look at a practice problem for section 12.5. And what I could do on that, what I'll do on that, on 19 through 25, I'll just scan the answer sheet and post that. So if you do decide to practice it before you take the test, or you need it for reference, how's that sound? Since we're not going to go over them. Okay. Otherwise, I will see you Wednesday. I'll post that test. Like I said, realistically, it's probably going to be Sunday before I post it.
And it'll be due Monday night, the
End of day Monday night. Yeah, end of day Monday, however you want to say that. And I will also get the videos. Actually, I'll probably get the videos up before all that.